Today's AI landscape is filled with questions about which frameworks, libraries, and tools to use for building agent-based systems and agentic workflows. As a result, developers and organizations find themselves caught in a maze of options, seeking the right approach to agent architecture. However, I believe these questions will soon become less relevant. Given the current pace of AI advancement, we're approaching an inflection point where we will no longer manually program agents and their interaction patterns. Instead, this complex orchestration will be handled by a new class of meta AI systems that can design and optimize agent architectures autonomously. In this presentation, I'll demonstrate how we can create such self-organizing systems through a strategic combination of distributed AI, reinforcement learning, and generative AI. This approach enables the development of autonomic systems that can adapt, evolve, and configure themselves to meet changing requirements. Let's begin by examining the foundational architecture that makes these self-designing systems possible. If we were wondering how modern AI systems will look in the future, we no longer need to speculate. Today's AI systems are rapidly evolving toward agentic architectures, software that acts autonomously on behalf of its creators. This shift isn't accidental. Over 20 years ago, while pursuing my PhD, I built early prototypes of such systems consisting of a number of components, where each operated as an independent actor, could learn, adapt, and cooperate in real time to enable system-level intelligence. Since then, these systems have never ceased to amaze me with their potential to exhibit true intelligence. What I mean by true intelligence is their ability to spontaneously self-organize and self-optimize their internal structure to deliver required tasks through local interactions and co-adaptations. Bear in mind that all that was done without pre-programmed rules or strategies encoded at design time. As we are yet again entering an era of agentic AI, this approach is now becoming the cornerstone of modern AI that, coupled with large language models, can revolutionize how we build intelligent systems. These models provide sophisticated reasoning capabilities that, when combined with multi-agent architectures, create systems with emergent properties, where the collective intelligence exceeds the sum of its parts. This synergy enables unprecedented levels of adaptability, problem-solving, and autonomous learning that were previously unattainable. But as always, there is a catch. The truly agentic systems that possess a high degree of autonomy are not cheap to build using existing software engineering approaches. This is because these approaches prioritize predictability, where systems are built with hard-coded, exhaustive rules and layers of observability to enforce pre-programmed behavior. And that unfortunately leads to the problem. The more autonomy we demand from a system, the more costly it becomes to preserve control over such system. As a result, scaling intelligence under this approach becomes at some point unsustainable and leads to trade-offs between cost and quality. As tasks grow complex, development and maintenance costs may quickly grow exponentially. If you listen to the early feedback of companies that started deploying agentic solutions, you'll understand why they suggest building systems iteratively, starting with the least amount of autonomy and gradually expanding capabilities. Although I agree with this careful and iterative approach, I also argue that it shouldn't have to be this way. We should seek for a new way of engineering strategies that would allow us to unlock the full potential of AI at a reasonable cost. To understand this better, let's dive deeper into the process and identify key areas where we could lower costs without sacrificing systems' intelligence and autonomy. As an example, consider a case where we want the system to perform a task that automates customer conversation analysis in order to update the CRM system with information that can be further acted upon. The task consists of a number of specific steps. First, it transcribes the customer audio call, then it classifies the call into predefined categories. It performs in-depth analysis in cases where a complaint was identified. Finally, it stores the obtained analysis results in the CRM. In the next step, the abstract task declaration gets broken down into smaller, realizable subtasks and mapped into a task workflow that can be executed using existing services outlined on the right side of the slide. Here we can see that the whole task is broken down into the following workflow of specialized services: audio transcription, conversation type classification, complaint analysis, CRM integration. Finally, before the solution coded in the form of a workflow can be deployed into production, it needs to be thoroughly evaluated using testing environment. To achieve this, we follow an iterative cycle consisting of development, testing, and approval stages, through which, as a result of several iterations, final and business-aligned solution gets produced and deployed. So far, the process follows the proven software engineering approach to deliver modern software. However, here's an elephant in the room. Building AI solutions, although on the surface similar to traditional software engineering, is in reality far more demanding and complex. This stems from the fact that AI solutions utilize powerful, yet unfortunately non-deterministic large language models that are susceptible to hallucinations and thus prone to providing incorrect information. As a consequence, significant effort needs to be put into aligning those models with business requirements through extensive testing, observability, and monitoring techniques, as well as significantly more complicated and iterative fine-tuning to identify the best combination of prompts, models, and their internal parameters. We are seeing the rising importance of AI engineers and advanced AI ops that aim to automate above described process as much as possible. Yet as the solution complexity increases, so does the engineering burden. All this means that treating AI systems as mere variations of existing software architectures and thus developing them by following traditional software engineering principles will soon reach its limits. More advanced AI solutions will simply become too costly to build using these approaches. As a result, rather than continuing to constrain AI's natural capabilities to fit our existing engineering frameworks, we should embrace an approach that leverages their true generative potential, not just generating human-like responses, but enabling systems to self-program and self-improve. What I am proposing is a fundamental shift, moving the burden of generating optimal system response from humans to AI itself. In the context of our example scenario, humans should only declare what they need in the form of a task declaration, an expected outcome, and approved solution that is generated by AI. The following slides outline in detail how we can bake in such self-organizing properties into software systems by combining distributed AI, reinforcement learning, and generative capabilities of large language models. The fundamental and core property underlying this approach is the capability of the system to self-optimize itself, that in our case is reflected as the ability to identify the optimal workflow configuration for a given task. Since we do not hard-code a number of potential solutions, but expect the system to discover them at runtime, we need to endow our system with the ability to perform a series of exploratory simulations during which, out of many potential workflow configuration permutations, the optimal one gets derived by the system. The workflow optimizer component manages this optimization process autonomously, employing a reinforcement learning-driven approach of trial and error. Verifiable rewards guide this exploration, systematically steering the system toward increasingly optimal regions of the solution space. To initiate the optimization process, the system must be able to generate and evaluate multiple alternative solutions. The workflow planning component is responsible for this task, leveraging the generative and reasoning capabilities of large language models to transform the task descriptions into diverse workflow plans. Importantly, the workflow planner coordinates with both optimizer and orchestrator modules to ensure that new workflow creation is guided by knowledge acquired from previously evaluated plans. This coordination also incorporates awareness of the agents available within the multi-agent system and the MCP services that can be employed as part of the agentic workflow. The application of large language models' generative capabilities extends further, When no existing agent or service can deliver the functionality required by the plan, the planner generates instructions for the workflow orchestrator to dynamically instantiate LLM-driven agents that did not previously exist within the system. This dynamic self-programming feature enables an emergent AI capability, spawning specialized agents on demand based on dynamically generated plans. This capability significantly enhances both the flexibility and diversity of alternative solutions. This in turn enables the system to automatically explore a much wider solution space than it would be possible through manual human effort. The right side of this slide displays an example meta prompt fed to the workflow planning module. This prompt contains all key information about the task, details of the agents available within the system, and specifications for the expected output. Additionally, it instructs the planner to generate 5 alternative plans and create new agents when the required capabilities don't exist within the current system. Example agentic workflows proposed by the planner are presented on the right side of the slide. These plans illustrate different strategies for generating more optimal system responses. For instance, Plan 2 attempts to improve conversation classification outcomes by introducing an ensemble technique that compares results from the 2 separate content classifiers. Plan 5 alternatively incorporates an additional transcript quality verification step. Agents with the suffix agent existing represent those already deployed within the system, while those labeled agent new indicate new agents that will be dynamically spawned at runtime. These new agents, being LLM driven, receive specialized prompt instructions from the planner that configure the large language models to perform specific required tasks. For example, the prompt content displayed on the right side, when fed to the LLM powering the agent, specializes it to conduct thorough analysis of conversation transcripts and extract detailed information based on the identified conversation type. Here is another example of dynamically created LLM prompt that evaluates and combines predictions generated by independent content classifiers using more advanced logic. In this case, the logic verifies whether both classifier outputs agree. If they don't, it applies further advanced reasoning to mitigate discrepancies and determine the correct classification outcome. The power of generative and reasoning capabilities of large language models truly shines in these examples. They demonstrate how the system can propose plans that extend beyond existing system functionality by leveraging its ability to self-program solution components when necessary elements aren't available. This represents a truly powerful emergent AI property with tremendous potential for generating solutions that were not pre-programmed or predetermined by the existing system structure. After multiple alternative plans are defined, the workflow orchestrator component executes these workflows in a simulation environment and collects performance metrics to evaluate their effectiveness. This simulation environment consists of a multi-agent system. After that step, the execution results are fed into a workflow evaluator component that uses reward functions to assign performance scores to evaluated workflows. These results are then passed to the optimizer component to perform another optimization cycle. Reward functions are one of the most critical parts of the described optimization process and can be defined manually or partially automated using the LLM as a judge approach. These functions play a critical role in guiding the entire reinforcement learning process and need to be thoroughly evaluated to ensure they align with expected business outcomes. When all previously described components are integrated with a multi-agent system in the form of a self-organizing feedback loop, most of the human effort associated with building agentic workflows can be delegated to machines. These systems will continuously seek to improve and optimize their own functioning. The approach to engineering AI systems presented in this video fundamentally transforms how we interact with these technologies, demonstrating how fine-tuning and specialization processes can be automated at the system-wide level. By shifting our perspective toward developing systems with self-improving and self-programming capabilities, we unlock new possibilities for scaling systemic intelligence to tackle complex tasks while simultaneously reducing development costs. And this represents a significant advancement over traditional engineering approaches.